Hi, here's my report on the third lab assignment. In this, we will analyze the motion of a star of given mass and use Newton's second law and the momentum principle to determine the mass of the black hole about which the star is orbiting. The momentum principle relates the rate of change of momentum and the net interactions of the system. The two components of this change are represented as the rate of change of magnitude, which is the parallel component, and the rate of change of direction, which is the perpendicular component. We can equate each component to the net force acting in that direction respectively to obtain F net parallel and F net perpendicular. Let us move on to the model for obtaining the mass of the black hole. The mass of the star and the time step delta t are entered as specified. I also specify the position of the black hole, which is assumed to be at origin. Next, I enter the relation to calculate the initial and final momentum of the star. The relations for parallel and perpendicular components of the net force, as discussed earlier, are also included in the code. In order to calculate the mass of the black hole, let's specify the black hole for visualization as shown. We can now use the formula for gravitational force to calculate the mass of the black hole. Here the vector r is the distance between the star and the black hole. We can add the respective lines of code to the model. Finally, a suitable arrow scale is specified and the mass of the black hole is added to the print command to obtain the calculated value in the output window. We can now run the module and analyze the results that we obtain. We can observe that the mass of the black hole is calculated as part of the iteration in the code. There is negligible difference between the calculated mass at each iteration, since the net force and distance between the star and the black hole change in proportion to each other. We can note this by observing the arrows representing the force components in comparison with the motion of the star. The value of F net at each time step is calculated by the model, as seen in the output window. The values of F net parallel, F net perpendicular, and the mass of the black hole are obtained at the end. We can make a note of these obtained values. The mass of the black hole calculated by my model is 1.98 into 10 raised to 31 kilograms. The final value of F net is 3.05 into 10 raised to 26 newtons. F net parallel is 1.35 into 10 raised to 26 newtons, and F net perpendicular is 2.73 into 10 raised to 26 newtons. Let's assess the results in terms of the rate of change of magnitude and the rate of change of direction of the momentum. The momentum principle quantitatively relates the net force and the rate of change of momentum. However, these quantities are not the same. The net interactions in the system are related to the rate of change of momentum. The relation between the two quantities is like that of a cause and effect. The net interactions in the system at an instant cause a change in momentum. Therefore, the rate of change in momentum is the result of these net interactions. This difference between the net force and the rate of change of momentum applies to their perpendicular and parallel components as well. Both components of the rate of change of momentum are caused due to the respective force component. Though the momentum principle quantitatively relates the net interactions in a system to the rate of change of momentum, it does not provide any information about the forces that cause this change. If we replace the black hole with another one of different mass, we can tell the difference if the motion of the star and the position of the black hole remain unchanged. A different mass will result in a different value of the net gravitational force. Finally, we will obtain a different value for the net force and its parallel and perpendicular components. We can use this value of the net force to calculate the mass of the new black hole.